Hi everyone, this is Diana Sinton. I'm a project manager for iGuide and help coordinate our summer school activities each year. Today I'm excited that we're going to hear from one of our teams from last year's summer school, team number 2, talking about the work that they did under the direction of Dr. Manju Yu at Penn State University. We're going to be looking at, we'll be hearing from them describe their work using GeoAI for burn area analysis and fire risk mapping in the Pantanal Wetlands. We're using a regular Zoom meeting for this presentation, so you're in charge of your own microphones. If you could please keep yourself muted unless you're presenting at that time. This is being recorded, and once it's processed, it'll be up on the iGuide website along with all of our other virtual consulting offices. We're going to get started in just another minute or so as people continue to log on. So as I said, I'm excited to hear this presentation from one of the teams at our summer school. Our summer schools take place each year. It's a project-based activity where we follow the practices and inspiration of team science. This group, each team, 5 or 6 different teams work on projects for about a week, kind of an immersive learning experience. And I was excited at the end to hear from the group, the external evaluators who looked at all the materials that was produced over the summer school and the weeks after. And this was actually the team that earned the highest accolades from that external review group. So this was the lead team coming out of summer school last year. As I said, one more time, this is a regular Zoom meeting, so please keep your own microphones muted. And we'll have time for question and answer at the end of this. We'd like to have our VCOs be informal, but please, if you could hold your questions till the end. And if you need a reminder, put them in the chat space and we'll get to them at the end. And with that, I will turn it over to team 2.
Yeah, thanks for the introduction, Diana. Hello, everyone. I'm Fatemeh, and I'm part of Team 2, which is led by Dr. Yu. Today, we are so excited to walk you through our project focus on the use of GeoAI for burn area analysis and wildfire risk mapping in one of the most ecological important wetlands, the Pantanal. Next slide, please. The Pantanal wetland is an extremely biodiverse region, but in 2024, it experienced a significant early season wildfire. This fire was not just sudden, but it was also intense, driven primarily by prolonged drought condition and rapid land use change in that region. So as a result, this even raised serious concern, which prompting urgent question about how we can better predict and respond to such events. And 2 critical questions emerged that shaped the direction of our research. The first one was, how do environmental and land use factors influence burn extent? And the second one was, can GeoAI enhance earlier stage fire risk mapping to support proactive management? To answer these questions, we needed to design a framework that could not only predict burn areas, but also understand the spatial and temporal drivers behind fire events. However, as you might expect, that we encounter a few major challenges. One of the most significant challenges was the highly imbalanced data set, meaning we had far more observation of unburned pixels than burned ones. And this make it difficult for many standard models to learn meaningful patterns because they are biased toward the majority of class. And in addition, we were working with just a single dry season's worth of data, which limited the variability we could capture in our model. And finally, the spatial and temporal patterns of the burn events were not tightly aligned. fires occurred in scattered locations and at various times, making it difficult to model them using traditional static approach. So we took a step back and began to strategically brainstorm around a few core design questions that could help guide our modeling efforts. First, we think about that. How could we incorporate both spatial and temporal context into our models so we don't just treat each pixel or location as independent? And second, what kind of models are capable of capturing complex fire behavior patterns and generalizing to unseen regions or future seasons? And third, how could we use feature engineering, including physical, environmental, and historical data to improve predictive power? With this design question in our mind, our team pursued two main modeling approach. Our first approach was to establish a baseline using tabular data. We built classification models, specifically using random forest and XGBoost and TabNet to predict burn versus non-burn area using a range of physical and environmental features. And this includes vegetation indices, temperature, land cover, and other special features known to be correlated with fire behavior. To enhance this baseline, we added additional layers of information, and one important step was integrating fire history data. For example, we computed features that describe how many pixels within a 5 by 5 window had burned over the past few days, essentially providing the model with recent fire activity trends around a given location. And this special context helps the model understand the fire spread behavior. And lastly, we include the Earth embedding from Alpha Earth, a pre-trained geospatial foundation model, which allows us to inject additional environmental context into our model. And this embedding capture latent features of the land surface and help us to incorporate broader physical and ecological conditions beyond the just input variables. In parallel, we pursued more advanced spatial sequence modeling approach. Rather than treating pixel as isolated point, we created a sliding patch that represents small area over time, which capturing the dynamic of how fires develop and spread within the neighborhoods. And this framework, each sampling our data set is not just a static point in space, but a sequence of observation collected over the previous few days across a localized region. And our goal was to predict whether the center of that patch is likely to burn in the next step not. So now it's a good time to hand it over to my teammate, Danny, who will walk through the rest of our presentation. Thank you.
Thank you, Fatima. And let's start with the basic feature sets, which form the foundation of our wildfire prediction model. What you're seeing here are a series of spatial grids that represent the key environmental and meteorological variables influencing a fire behavior across the landscape. These include land cover, which captures vegetation type and human disturbance, elevation, or DM, which shapes drainage and wind flow, near surface temperatures and dew point temperature, which together control humidity and fuel drying, and wind components, both east to west and north to south directions, which strongly influence how quickly a fire can spread once it starts. We also incorporate surface pressure and total precipitation. These variables help describe how much energy and moisture are entering or leaving the surface, which affects ignition potential and the persistence of fire activity. All these datasets were harmonized onto a common spatial grid covering our study region, southern Amazonia and the Pantanal Wetlands. This harmonization step is important because it ensures every layer aligns in space and time, allowing the model to interpret them as unified environmental snapshots rather than disconnected datasets. Together, these features serve as environmental backbone for our models, providing a consistent baseline from which we can start to understand where and when fires are most likely to occur. Next slide. Next, we add dynamic fire history features, what we're calling the previous burn features. Each map here represents a lag period from lag 1 through lag 5. These layers show how recently each grid cell has burned, effectively telling the model where a location experienced fire yesterday, 2 days ago, or several days earlier. Clearing these features helps the model capture temporal memory. For example, if we look at the images, we can see that areas that burned are often near cells that had burned previously. This spatial temporal continuity is common in wildfire systems where fire spread can advance incrementally across neighboring cells. This effect is especially strong in the Pantanal where vegetation is regrowth and fuel buildup follow distinctional seasonal cycles. After a fire, the region experiences a recovery phase. New vegetation grows during the wet season, fuel dries during the dry season, and eventually conditions reset to the next fire. So while the basic features describe the potential for burning, the fuels, climate, and terrain, these lag burn maps capture the recent dynamics of fire on the ground. Together, they provide both spatial and temporal context, helping the model recognize patterns of ignition, spread, and regrowth. Next slide. Off-Earth is a pre-trained Earth observation foundation model that processes multispectral satellite imagery and learns how different surfaces reflect light. And then condenses that information into numerical embeddings, compact, information-rich features that summarize landscape characteristics such as vegetation density, soil moisture, and even subtle texture differences across terrain. Each small panel here represents one of those embedding dimensions. Red and blue areas indicate relative activation strengths, in other words, how the model internally perceives variations in land surface properties. The advantage of using embeddings is that they encode complex spatial and spectral relationships that our basic variables might miss. Instead of feeding in individual spectral bands or indices, we're using features that have already been optimized by a model trained on global satellite data. In practice, that means that embeddings serve as compressed knowledge layer. They bring in global context, learn from years of satellite observations, and make it available to our local model. This allows our wildfire predictions to generalize beyond the relatively small set of labeled fire observations that we have on the ground. Next slide. Here's how those different features combinations perform under baseline conditions, where we train on the dataset and on 30% of randomly sampled observations. We compare three algorithms, random forest, XGBoost, and TabNet across three configurations. First, basic features only. Second, basic plus previous burn features. And third, basic plus previous burn plus alpha AI embeddings. Across all experiments, XGBoost consistently performs the best, reaching an F1 score of 0.97 with the full feature set. Adding previous burn information improves recall, meaning that model becomes better at identifying actual fire events rather than missing them. Adding the alpha AI embeddings further improves precision, reducing false positives and producing more stable results across time and space. TabNet, a deep learning architecture designed for structured data, performs reasonably well. Doesn't quite reach XGBoost efficiency. Random forest, while simpler, still shows steady improvements as new features are added. The key takeaway is that each added layer of information improves model skill, moving from an F1 about 0.84 with the basic features to 0.97 when embeddings are included. That's a substantial gain. Nearly a 15% increase in predictive performance, and it underscores the value of combining physical, temporal, and learned spatial features. Next slide, please. Finally, this slide looks at one of the most difficult prediction challenges, a single-day forecast in the case June 16, 2024. Instead of a random sampling, we're asking the model to predict fire occurrence on a day it hasn't seen before. This tests the model's ability to generalize not just in space, but in time. Here we see the performance drop sharply across all models. Even the strongest configuration, XGBoost, with all the features, achieves only an F1 score of 0.13, while random forest performs slightly better at 0.17. This reduction happens because a single-day fire activity depends on very transient conditions, a lightning strike, a sudden wind shift, or human ignition. That may not appear in the daily average environmental data we provide. Essentially, our model knows where fires are likely, but not precisely when they will occur. Thank you, and now I'll pass it off to my colleague, Bikas.
Thank you, Daniel, for your informative talk. Hi, everyone. My name is Bikas, and I'll be mostly talking about the results. So, building on the model architecture and the feature sets just described, my focus is on how well our models perform in the critical early stages of fire risk prediction in the Pantanal. While the overall performance metrics were high, predicting fire risks for a specific day is far more challenging, as there are highly imbalanced data, which we can see in this slide. There are more no-burn pixels compared to the burn pixels. This slide mainly focuses on mid-June 2024, which is an early dry season. On the right-hand side, we can see a ground truth burn that shows very small, distinct burn patches. When we used only basic feature sets like topography, land cover, and weather, the models predicted burn at the center map we can see covers a very vast diffuse area. The model struggles to precisely localize the burn risk and predicts many false positives along with blocky regions. Next slide, please. Then we introduced previous burn history as a spatiotemporal context, and we immediately noticed that the dramatic improvement in the overall predicted burn at the center map. The predicted patches are now more tighter and better aligned with actual ground truth. The spatiotemporal context of previous burn days significantly improve the burn location predictions. Next slide, please. We also found that adding alpha AI embeddings further refined the predictions. This slide shows the results using our high-performing XGBoost model with all the feature sets. The alpha AI embeddings, which potentially capture latent environmental status like fuel conditions, improve the numerical prediction performance. The predicted burn area at the center is now even more contiguous and accurately traces the actual burn scars. This embeddings improve the prediction accuracy, possibly by representing the prior status of land cover at that year, and help to fill the gap of the missing fuel status data. Next slide, please. We also did a feature important analysis. This feature important analysis results confirms our visual findings. The top left-hand side graph shows that topography and soil moistures are the most important basic features. However, once we add the previous burn histories on the right top side graph, the feature named lag_1, that stands for burn status from the previous day, becomes the most important predictive feature. This dominance holds true even when adding alpha earth embeddings that clearly visible at the bottom left-hand side graph. The absolute importance of previous day's burn status suggests that the fire progression is highly dependent on recent events. This leads us to a clear outlook that an autoregressive architecture that explicitly uses this temporal dependency is the most promising way forward for operational fire prediction model. We can also see that among different models, the importance of different features doesn't fully align with each other, but our main focus was to look at the interaction of different features and how they play an important role in the overall fire dynamics. So that was it from me. Thank you, everyone. So now I will hand over to Jiyeon to cover up our sequence model results. Thank you.
Well, thank you, Bikas. I'm Jiyeon, and what we've done so far is discussing our baseline models. From now, I'd like to walk you through the idea behind using a residual convey LSTM model for spatiotemporal prediction, specifically in the context of fire burn progression. First, let's talk about the modeling goals. Our main objective is to capture short-term temporal dependencies, things like heat waves, drying trends, and other conditions that evolve over just a few days. At the same time, we want our model to understand the spatial context that includes neighboring burn areas, terrain, and vegetation, all of which strongly influence how a fire spreads. Now, why does this matter? When predictions are embedded in a spatiotemporal setting, the model can actually learn how fires progress rather than treating each pixels in isolation. This allows it to capture important dynamics like how burn scars expand under certain wind or fuel conditions. Traditional single pixel models miss this context, which means they often fail to identify meaningful progression spatial temporal patterns. Our approach addresses those limitations. Here's on right side of our slide. Here's a quick look at the burn progression pipeline that supports this modeling. We start by loading daily CSV files, including our several features, and converting them into burn maps. From these maps, we extract burn patches and filter them so we are only keeping cases that truly show progression. In parallel, we stack sequence of 5 consecutive days to give the model the temporal window it needs. Once everything is processed, we can visualize the burn progression, helping us better understand the patterns the model is running. Next page, please. So according to the next page, before talking about this result, let me quickly talk about the key difference between baseline models and sequence model based on the Convey at STM. The baseline predicts at the pixel level, while the second approach with Convey at STM works more at the regional or raster level. Both uses spatiotemporal information, but Convey at STM does it in a more explicit way. I mean, it better captures what's happening in the surrounding areas. Now, if you look at this figure, you can really see the difference. The baseline we already saw gave us a little bit scattered, spotty predictions, while the Convey at STM produces a more continuous spread like this. This is actually much more realistic for wildfires, since fire tends to spread smoothly across areas, not in isolated patches. Next page. So this is what I done so far about introducing our second approach. Next page, please.
Thank you, Jiyeon. So where to wrap up, like what we have done. So we have built 4 different models, and for each of which we conducted several experiments with a different output. Basically, we talked about the baseline modeling that include the random forest, the XGBoost, and the tabular, the TabNet, and these are the tabular models. And then we have also the sequence modeling, that is the convolutional LSTM. For each of which we tested the basic feature, and then for the tabular one, we added the burn history manually, and then for lastly, we also added the embedding. And what we have learned, what we were able to accomplish, is that we predicted early stage fire risk at satisfactory accuracy with test data. But when it comes to running this for the next day fire, we have a lot of fine tuning is required to make it more operational. But what we learned is basically with burn history is among the most important predictor that we observed, and we will come into what are we building on that in a bit. And then the second thing, that with embedding alpha AI improved our prediction, possibly capturing a prior status of land cover at that year. So where is that direct us, and what is need to enhance the fire prediction with that? First, with looking at how burn history improved, that's confirmed that autoregressive architecture could be a very promising way forward for operation. That is the convolutional LSTM. Then also, like including feature like AI alpha embedding has a great potential to improve model generalization, but there is also some consideration that we account for regarding like interpretability of these, and also the temporal frequency, because these are, after all, capturing only one snapshot for each year. So moving forward and building on what we have been doing, so we will be focusing next on using the convolutional LSTM with the basic feature, including the alpha earth embedding. But also we will be adding some other several improvement toward our model, and that will include like replacing the modest parent area that we used in our previous work with the active fire prediction. That will allow like to improve the temporal resolution and capture near real-time fire dynamics as more realistic prediction. We will also extend the data collection period for broader temporal coverage. We already collected our data for 7 years now, and that's include all season, not just the dry season. And we will be also including the alpha Earth into the convolutional LSTM. This is tips we didn't have enough time to work through it during the summer school, so we will be doing that next too. And finally, we will be also adding the NDVI as an additional input variables to incorporate vegetation health, especially that it will cover higher temporal frequency that is not covered in alpha Earth embedding, for example. And with that, we will wrap up and thanks our leader, Dr. Yu, and NSF and the iGuide team for this great opportunity. We are happy to take any question.
All right. I know that Dr. Yu is proud of it, of all of the work that you all did, and is excited right now. I will have some questions, but let's see if anyone in the audience would like to use their microphone and ask a question and you can also type something into the chat if you like. That's the whole group. We've got a nice team picture there at the bottom. As I said before, this year, I think we had about 26 students participate, all PhD students this year, which was an unusual characteristic of the cohort. Our summer schools up for the last 3 years have taken place in Boulder, Colorado, and you can see some of the Flatiron Mountains there in the background in Boulder. We will have a 2026 summer school. It will not be in that venue. It's actually going to take place at University of Minnesota, and that will be in the middle of July next year, and that'll be the final iGuide summer school, at least under this current round of funding from the National Science Foundation. So we've got a question here that I will, wondering how you incorporated Alpha Earth into the daily prediction, given AEF has a 1-year capture. There's someone who'd like to.
I could handle that. So this is excellent question, and this is what we were talking about the limitation with the temporal resolution with Alpha Earth, because it is only compressing a 1-year data into one single temporal dimension. So it doesn't have, it's not incorporated as a daily variable. It is incorporated as a static variable for each year. I hope that answered the question.
All right. It was Alpha Earth was just released just before our summer school in the summer 2025. So that I know I had an influence on several of the teams and their workflow ideas. While we're waiting for another question, so I kind of remember from your presentations and talking to you all during the week. I'm going to hold that question because I want to make sure we get the audience ones here too. Do you produce burn area on daily temporal resolutions?
Yes, the answer would be yeah. The mode is burn area that gives us a data set for a month, which has information for each day. So we extract it and make it a daily burn data set.
For those of you interested in some of the details about this group's work, there are versions in the iGuide platform. There's a version of the notebook that this group had produced. It could be a little bit dated right now with some of the things that they might have added to it since September, but at least there was a September 2025 working version of the Jupyter notebook that team had generated. So at some point, I'll share the link to that. It's one of the deliverables that the iGuide summer school teams produce so that we can, one of the ways that we have to extend the reach of the activities that we do. And that platform has both data sets and notebooks and open to anybody if you're able to log in with an academic university affiliation or many others as well. So I remember from the very beginning that some of you have had more familiarity with some things around wildfire, maybe in a US context or internationally, or others of you came from more of a modeling background. How did it, if you could just say something briefly about the knowledge sharing that you experienced over the course of the week? Was there a little bit of, especially for those of you without any background in fire dynamics or fire modeling, how did that go?
Yeah, I can start talking a little bit because my experience with fire was very brief when I started with this project at the summer school, and I think was one of the very nice things about like bringing this diverse group together and like just bringing idea from entirely different perspective and trying to make synergies between us all together. So sometimes we get into like ideas that seems far away from where we are at the moment, then like as we discussed, like we find like common ground to implement. Some of these were like were we able like to pursue and like incorporate in our project. Some like just were left out as just idea during the school, and I think that was one of the very rewarding things about this experience from my perspective.
That's nice. It's nice to hear those reflections. Anyone else want to comment on it? There's the week you think you might have learning from others in Colorado or at the summer school, and then there's the week that you do have. And I know there are things outside of our that we can control and that we can't control. There were issues. We had some issues with even some computing access on that first day, I remember. Any other questions from the audience? Dr. Yu, do you have a question that you want to pose to the group? If you're still here with us.
I think they did a great presentation. I also think that they updated their future work pretty well. We're working together we're meeting every other week for a updated result out of the summer school. So to be expecting a publication out of this, and that's very exciting for all of us.
That is exciting. Yeah, definitely not anything, we're always excited to hear when those type of synergies happen and to make these professional connections, because all of these students are from different universities. So it's bringing everyone together that you might be able to click in the right way professionally to work on something like that. That's exciting to hear. Well, we will keep monitoring. iGuide is excited to hear about the work that you have done and your future plans. We look forward to following your publications and helping promote them. Again, let me put for any of you online, let me quickly put here's the iGuide link to our summer school 2026, which right now only has a placeholder for the place and the dates. It's going to be July 13th to 17th, 2026. We will again be following a similar team science approach, but all of the problems themselves are yet to be determined to see how that might work out. Also, please remember that the platform, let me get this link for the platform. Our platform is available for anyone to log into, to see the resources that are here, to be able to find the notebooks and data sets that people have used. It's iGuide's great commitment to support open science and enable as much reproducibility and replicability as we can. So if there are no more questions, we will wrap this one up. I want to thank Team 2 again for pulling this together, taking the time at the everyone is always busy at this time of the semester, and we really appreciate your getting yourselves organized to put this on together. Thanks very much, everyone. iGuide thanks you for your participation, and we'll talk to you soon.
Thank you.
Take care.
Thank you.
Yep, bye-bye.
Thank
Thank you,
you.
everyone.
You.
Good one.